Hello, good morning. Of course, first of all, thanks to the organizers to give me the opportunity to present the work here and for organizing this conference here in Bilbao. I'm going to talk about geometric phases. In particular, a kind of geometric phases which are the topological phases. Okay, and mainly in a generalization of the standard geometric phase, which is called a Uhlmann phase. Okay. So to explain you the concept of the Uhlmann phase, I need to make a connection with the standard Berry phase that maybe most of you are familiar with. But just in case, let me introduce the. This is not working for some reason. Okay, this is the outline of my talk. Okay, let me explain the idea of the Berry phase in very geometric terms. So what we have, when we have pure states, so we have the state of physical, or the set of physical states, which are basically projectors, and over each projector we can draw a line with a fiber, which is called a fiber, which is connected with the Hilbert space of state vectors, right? In such a way that if I moved over the fiber, I may change the phase, right? I change the phase by moving on the fiber. So now consider that we have a trajectory on the state of pure states. But there are many trajectories on the state of vector space, of vector states that projects to the same trajectory on the physical states. So, but the idea of Berry was to introduce a condition in such that if we pick some representative state vector of this projector, then the next one, the infinitesimally close one, will be the closest one in the sense of the Hilbert-Smith of the Hilbert distance. So basically, instead of taking something over this or over this, just the closest. In this case, this means that both state vectors are the relative phase is 0, basically. But now consider a closed trajectory. Okay, so we have a closed trajectory over states of pure states. And we impose this parallel transport condition, this Berry condition, over each point of the trajectory. Okay, but then it might happen that when we come back to the initial point, to the initial physical state, there is a difference between the vector, the state vector, the initial state vector, the final state vector, right? And this difference is a phase. Okay, and this phase is what we call a Berry phase. Okay, which is basically the argument of this inner product, which is written like this, and this is what is called Berry connection, right? So this is just this is a gauge invariant. Gauge meaning that we can change the gauge, the phase here over the trajectory. That we can make a instantaneous phase rearrangement, and the final mismatch, if you want the final phase, will be invariant. So it is a gauge dependent. It's independent of how the trajectory is covered. I mean, for example, how fast the trajectory is covered. Usually, when doing this kind of trying to observe these phases experimentally, one takes the advantage that when we make an adiabatic transformation, the parallel Berry condition is automatically satisfied, it's approximately satisfied. One could make the transportation using whatever parameterization or with whatever speed, as far as the Berry parallel condition is satisfied. So it is an intrinsic property of the trajectory. It can be measured as any phase in quantum mechanics by using interferometry or something like that. And in 1D, I mean, we only have the one space with one dimension. The Berry phase, because it's a trajectory over the whole space, is a kind of a global property, which is related with the topology of the space. I will come back to this point afterwards. So, okay, this is for pure states, but what about general quantum states given by density operators? Is there some way to define a geometric phase, something similar to this? In such a way that can we define something similar to the Berry phase in the presence of temperature of noise that in this situation we need density operators? The answer is yes. And the answer is not unique. But the first approach to this is due to Armin Uhlmann. Uhlmann is the first, is known also for this Uhlmann fidelity that most of you are familiar with, which was done in 1986, right? As just a mathematical construction. And the idea of the Uhlmann phase is based on what is called Uhlmann amplitudes. What is an Uhlmann amplitude? An Uhlmann amplitude is basically are constructed using the fact that any density matrix can be decomposed like this. Well, this is a complex matrix, right? A complex operator, an operator, right? And these operators form a Hilbert space with this Hilbert-Smith product, okay? And what is the physical meaning of this? This is nothing but the idea of purification. Nothing but the idea of purification, right? If I write the amplitudes in a basis, and I make a correspondence with a map that just basically flip this bra in this get, then I map these matrices to states on a larger Hilbert space, which are essentially purifications of this density matrix. And the inner product is just the inner product of purifications. Okay. Okay, I'm going to still using amplitudes, despite that this connection is going to be necessary to make a measurement of this quantity, right? So, well, okay, this is the idea that we have pure states in a larger system, but if we see a part of it, we see a density matrix, right? So, now consider the space of this, the space of this equation. I mean, the space of amplitudes. This equation is invariant, and there are transformation of W to W times some unitary, right? It's invariant. So similarly to the pure state case, when we have here is a structure when we have a density matrix set, the set of density matrix, and over each crossing this, so to say, this set of density matrix, some fiber, okay, which has a freedom which is a unitary. I mean, if I move on the fiber, I change the unitary, but the density matrix is the same because this equation is invariant. Okay, so now the same idea as the very phase was that if I have a trajectory over the set of density matrices, then several trajectories are possible. Here in the state of amplitudes, then what Uhlmann proposes to take the adjacent purifications to be the closest in the sense of the Hilbert-Smith distance. I mean, in the sense of the distance of the Hilbert space where these amplitudes live on, right? And this is what is called the Uhlmann parallel transport condition. Okay, but then if I close the loop, if I make a transportation around a closed loop, then it may happen that when I come back to the initial physical state, then I do not stay in the same amplitude. They differ in this case, but by some unitary. Okay, and then this is what is called unitary. That's holonomy. This is the holonomy of the path, and the Uhlmann phase is defined in similar terms as the very phase as the argument of the inner product between the initial and the final amplitude. Right? It can be written like this, where this is the path ordering operator, and this exponent is what is called Uhlmann connection. Okay. It's also gauge invariant, of course, by construction. Then what kind of I mean, how is this object here, this Uhlmann connection, how it does look like? So it is difficult to obtain a closed expression for it, but Hübner gave a closed expression in terms of the instantaneous eigenvalues. For here, I mean, k is the parameter that is going to be transported, okay? And but then, if we want to follow the Uhlmann parallel transport condition, the unitary that has to be applied infinitesimally is basically the path ordered exponential of this term here, right? But in the case of two-level system, this is much more simple, which is basically the commutator of this derivative of the square roots of density matrices. Okay. And very important is that in the pure state limit, when we have pure states, and if we follow this approach, when we have pure states, the Uhlmann phase equals the Berry phase. So it's a faithful generalization. Okay. So to summarize, it is defined for general pure state, for general quantum states, not necessarily pure. It is gauge independent. It's independent of how fast the trajectory is covered. It's an intrinsic property of the trajectory. For pure states equals the Berry phase. Can be measured. There is a measurement of 2011. And in 1D, then this Uhlmann phase is also a global property. So let's explain this a little bit more. Okay, consider these phases are particularly useful in systems with what is called symmetry-protected topological order. I guess that most of you are familiar, at least a bit familiar with it. Basically, when we have, in this case, so suppose that we have a free fermion system with some Hamiltonian in 1D. So K it lives in 1D. So the Brillouin of this K is just a circle. Okay. Then if I take the one particle state of this Hamiltonian and I make a transportation over the Brillouin and following the Uhlmann parallel condition, then what happens is that this Berry phase becomes quantized in units of pi. It can be 0, it can be pi, right? So this is what is called topological because this is split two different phases. To call it, I mean, trivial topological phase and non-trivial topological phase, but this is just a matter of convention. Most of the cases, not always. But the point is that there are two different topological phases. Why is topological? Well, you can think about the topology of this thinking in the following. This Hamiltonian here may depend on some parameters, some other parameters different from K. And then I may change the parameters a little bit. I can deform that Hamiltonian by changing the parameters. And then I will change these vectors, and then I will change the trajectory. But as far as the transformation is smooth, the phase, the Berry phase, in this case, is going to be in the same value, 0 or pi. So that is the reason why, we call it topological, because it is quantized. So it is a property which is quantized and keep invariant under smooth transformations. So, okay, now we have density, a geometric phase for our density operators. So we approached several years ago, a few years ago, the possibility to study the topological properties with the Uhlmann phase, right? And in this case, we consider that this system with symmetry protected system have some temperature, such that we consider the transportation of the density matrix given by the Gibbs ensemble. Okay, this was done for a level with 2 internal degrees of freedom. For example, typically with a system with 2 bands, right, in 1D. And this is the gap between the bands. We depend on K, and this is temperature, and this is a unitary vector on a unitary vector and the Pauli matrix, and the Pauli vector. So it happens that the Uhlmann phase becomes also topological. It becomes quantized. It becomes quantized. It's split to different topological phases, and this is so even that we have non-zero temperature. So we have an observable which is quantized even in the presence of temperature. Okay, this does not happen with conductivity and other typical quantized properties. Okay, examples when this is so we have applied this formalism. The first example is this model of SSH model of polyacetylene, which is basically a 1D chain of fermions that we have two different phases. So this phase, okay, when J equals 0 as a limiting case, and the other limiting case is when J1 is 0. So we have two different. Those are different. I mean, those are different topological phases because these are like topological defects. So they live on the unpaired on the edges. So if we compute the Berry phase and the Uhlmann phase in particular for this case, the Berry phase is just 0 temperature here, and we see that we differentiate both phases the same as what was known. And what we see with the Uhlmann phase is basically that there is a critical temperature. There is a critical temperature that inside this volume, the Uhlmann phase remains pi in one phase, and for some if we are approaching to some temperature, there is a sharp transition between 0 and pi in this observable. So it's a temperature which is not 0. This is also the case with another example, for example, with the Majorana chain that is very similar to the previous one, but with Majorana fermions unpaired on the edges, on the ends of the chain. And this is what we find. Okay. And also with this model, which is basically a ladder with different with a magnetic field, which is called Kroch ladder, which is due to Michael Kroch, and this is the example here. Okay. And the question is that this is fine, this is theory, but can we observe? Can we measure these properties? And the answer is yes. This is the paper that we have done, which is basically based in the IBM quantum experience, what was I mean not the one that is running right now, but the one that was running in January of last year. That was of 5 qubits. And what we did is simulate basically. Okay, we do not have control in condensed matter systems to see these phases, but we can simulate these phases in a quantum simulator, which is just 5 qubits simulator. In this, basically, this is the circuit that we follow. It's basically is designed to follow the Uhlmann parallel transportation. This is the system that we coupled it to an oscillator to create a purification of the system such that the system is in this mixed state. Then these states are the ground and excited states of some Hamiltonian, okay? With two different phases such that the Uhlmann phase is quantized, 0 or pi. So as far as m is smaller than 1 and r is smaller than this or is larger than this, the Uhlmann phase is pi, otherwise it's 0. Okay? These are the results of the experiment. And these two plots correspond to the case of the system following the Uhlmann parallel transport. We see that there is a theoretical value, the blue dot line, and this is a simulation taking account typical source of errors, and this is the measurement results. Okay, this is a comparison of the relative phase between adjacent purification that you see that they are very close to 0. And this is another approach, most in the spirit of a quantum simulation, which is not following exactly the Uhlmann parallel transportation, but it's a modified protocol in such a way that if we do not know exactly the initial state, we can use the quantum simulation to compute the Uhlmann phase. Okay, to use it like most in the speed. Okay, this is was done for 1 qubit, but this is. We have this in mind to extend it for larger systems. So okay, those are my conclusions. So that's geometric topological quantum phases for density matrices. I think this is an interesting topic. I have explained the Uhlmann phase, in particularly for the case of 1D symmetry protected topological systems. This Uhlmann phase has some critical behavior with the noise and temperature. There is a critical temperature. And we have observed this critical behavior with the IBM superconducting qubit platform. And there exists extension of this approach to these systems, okay? But I don't have time to explain. So these are the members of the collaboration, from myself and Professor Martin Delgado from Complutense University, Oscar Villuela, who was a PhD student in the group, but now is in MIT and Harvard, Stefan Philippe, which is in IBM in Zurich, and Simone Gasparinetti from ETH, Andreas Barras, who is here in the audience. And those are the references. So with this, yes, thank you for your attention.
Time for one quick question.
Thanks a lot. Can you say more about the stability of edge modes at finite temperature settings of the type you discussed?
Okay, the stability of the edge modes is not directly related with the Uhlmann phase. So generally, if we have, it depends of course, of the noise that you have in your system. So for a particular kind of noise, that is basically that keeps the structure, the block structure of the system. Then what happens typically is that noise you keep the edge modes, but you get some mixture, some thermal way. On the other kind of noises that mixes everything, typically edge modes decay. So typically edge mode decays. Yeah.
Another question over there.
It seems to me that the Uhlmann connection and the Uhlmann phase are rather directly connected to the quantum Fisher information matrix. Is that correct?
Sorry, say again, please.
The Uhlmann connection and the Uhlmann phase are rather directly connected to the quantum Fisher information matrix. The Berry connection is for a real pure state.
You mean for
it's the imaginary part of
you mean for holonomic quantum computing and this kind of things?
No, generally. I mean, my question is it correct that it's directly related to the quantum Fisher information matrix?
I mean, it's a coherence property of that. You need to have some coherence property in the. If I understood correctly the question, it is a property which is related with the coherence that you have in the density matrix. But the property, I mean, the relation with quantum information, I don't understand if.
You know the Fubini-Studi matrix.
Say again, please.
Fubini-Studi or study metric for pure states. This is the quantum Fisher information for pure states. You heard about that, or the imaginary part is the Berry phase. So I strongly expect that the Uhlmann phase is also related to.
I don't know.
Okay.
I don't know. We can talk afterwards if you want.
We can discuss this in the coffee break and switch to the next speaker.